In this video, we're going to start to look at lipids, our last major class of biomolecules. So we start with the most basic type of lipid you can have, and that's a fatty acid, which has a carboxylic head and a very long hydrocarbon tail. Now, most fatty acids are between 16 and 18 carbon. Anything less than 14 or greater than 20 inside of cells are really uncommon. Palmitic, oleic, linoic, and stearic are your most common. Now, when we count carbons, we start at the first carbon, that's part of your carboxylic acid, and you just move down 2, 3, 4, 5, etc., etc. You can also count carbons backwards if you give them the omega prefixure. So here's omega 1, omega 2, omega 3, and so on and so forth. Now, for biological fatty acids, over half the fatty acids in plant and animals are what we call unsaturated. That is, they have a double bond. So when we call about unsaturated and saturated, we're talking about the amount of hydrogens. If you're unsaturated, you have a double bond. While if you have no double bond, you have your maximum amount of hydrogens. You're saturated in hydrogens. Now, these double bonds happen between carbon 9 and 10, the first one at least. And the way that you talk about double bonds inside of a fat is that you call it delta 9. So this is saying delta, double bond at carbon 9. And a lot of the carbons are actually polyunsaturated. So they happen, if you have extra double bonds, they happen at every third carbon. So here's 9, 10, 11, 12. There's your second one. Or 9, 12, 15. So you'd say delta 9, 12, or you can just call it 9, 12, delta 9, 12, 15, or 9, 12, 15. If your double bond happens at your third to last carbon, that's what we call an omega 3 fatty acid. So here, 1, 2, 3, we have a double bond happening at the omega third position. This is an omega 3 fatty acid. Now, the double bonds inside of biological fatty acids are usually cis, and that's to help with sterics. And these double bonds give our fatty acids some interesting properties. So if something has a double bond, you can't pack your fatty acids as well. And so what happens is that you're more likely to be a liquid at room temperature. So here are 3 different types of fats you can cook with: olive oil, butter, and beef. So beef has the most saturated fatty acids, so it's more likely to be a solid at room temperature. Butter has less saturated fatty acids, so it's more of a soft solid, while olive oil doesn't have that many saturated fatty acids, so your side chains can't pack that well, and you're a liquid at room temperature. Now, inside of our body, our fats are usually in the form of triacylglycerols, or tags. And so what that is that you have glycerol, and you just add 3 fatty acid tails to make your triacylglycerol. And these are very nonpolar and water insoluble. And tags are your energy reservoir in animals, and it's your most abundant class of fatty acids. And tags can differ based on what type of tails they have and what they have on their head groups. So you can change both of these. And the fats and oils that we work with inside of the cells are usually a mixture of these different tags. And when you talk about plants compared to animals, plants usually have more unsaturated fats than saturated. As we saw in the previous slide, that olive oil is being liquid because it has more unsaturated tails. Now, the way that we store these fats is in adipocytes. And the reason why we store fats for energy is that they are highly efficient to store this energy. You roughly get 6 times more energy through a tag than you do through glycogen that we talked about in the carbohydrates chapter. One of the reasons is these are less oxidized than carbohydrates and proteins, but the big reason is that they're nonpolar. We can store these fats without water, which is great because if we have glycogen, for every 1 gram of glycogen we would have to store it with 2 grams of water, which is very inefficient when you're talking about lugging around these biomolecules for energy. since they're hydrophobic, we don't have to carry extra weight, which would just burn more energy. And so these adipocytes, they're basically just chock full of these fats. Men, on average, have 21% fat in these tissues, women 26%. And the amount of fat you have in you, you can survive about 2 to 3 months without eating. You'd get the energy that you need. While the glycogen in you, you have about 1 day's worth of energy before all your glycogen runs out. And that's it for this video. I will see you in the next one.